Hello and welcome to my third lesson on Statistics 2. In today's lesson, I want to take us through measures of dispersion, and the objective of the day is students should be able to determine the measures of dispersion correctly. And so let's begin. Measures of dispersion. In this particular lesson, I want us to target two things only. That is variance and standard deviation. The reason I want to target these because they are the major areas that are tested in KCC, and again also they are the major or the bulk part of the concept of measures of dispersion. I know there are some others there, but these are major parts of that. For us to begin, maybe I need also to mention that what we're going to be doing in measures of dispersion is just to determine variance and standard deviation. That's all we're going to be doing, and therefore we need to be able to know the following. Number one, when you're dealing with a group of a given data, we need to consider, is it ungrouped data or is it grouped data? The same thing also for standard deviation. We'll also need to find out, is it grouped data or is it ungrouped data? It's important for us to do that. And what I mean by ungrouped data is, say, when we are recording performance of students in, say, a maths cut, we could be having a case where only one student had 12, another student had 13, another one had 15, another one had 17, and on up to whatever figure. But if it was group data, it would be the case where we would have several students having 12, say 2, several students having 13, probably 5, several students also having 14, say 6, 17 students being, like 3 students having 17, and maybe one student having 18, and all that. That will be grouped because for every given value, we have several people who have that particular figure or answer. So that particular figure. So we need to always determine, is it group data or ungrouped data, so that we use the appropriate formula. Now, therefore, I need to mention that for grouped data, for ungrouped data, variance will be given a sum of d squared divided by n. For ungrouped data, it will be sum of fd squared divided by n. The difference between this formula and this one here is that this has an f, this doesn't have. This f is because we have several observations, several values for every observation. For example, we have, say, 3 students with 12. So in that case, we'll have 12 times 3, and on and on. But here, we just have a single student of 12, a single student of 13, and on. The small n implies that it's ungrouped data. The capital N means it's grouped data. It's just a rule in statistics. In this case, I also need to mention that the D really is deviation from assumed mean. Sorry, deviation from mean, arithmetic mean in that matter. So D will be just deviation from assumed mean. Another thing, as a summary for standard deviation, I need to say this. All times, standard deviation is just square root of variance. So I don't even need to get into the formulas for standard deviation and all that, since whatever thing we have, whether grouped or ungrouped or whatever type of question we're doing, standard deviation will always be given by the square root of variance, and that is a rule also in statistics. I need to delve a lot more into the formulas, and let me get into this. The first thing, I need to say that the sum of d squared divided by n, this formula here for variance of ungrouped data, is the same as this one. Okay, since I've just indicated earlier that d is x minus x bar. So deviations from assumed mean squared, adding them together, dividing by the total number of observations gives us variance. The next thing is, if we have this other formula that I had at the beginning there, that formula must be the same as this because of the same reason. D is just x minus x bar. Only that every time, this time, we're going to be multiplying every deviation with the respective frequency, add them all together, divide by total number of observations. The next thing I need to mention is that this formula here is algebraically the same as this one. It can be proved through algebraic operations to get that particular formula, and therefore I think this is easier to understand probably. Or when you're operating an actual question, you can choose between the one that you want, but sometimes I think this can be good, especially if the values do not give you big values. I don't know, the observations, if they don't give you big values, maybe this could be a good idea, since at some point you will calculate mean, and then you just need to square the x's and operate as the formula indicates. I'll get into an actual question therefore later on, and I'll show you what exactly I'm talking about there. Another thing, this formula, that same formula I just mentioned there, is the same as this one. The reason is the x bar, that is arithmetic mean, is sum of f of x divided by n. So that shouldn't shock you at all. So that's basically just a breakdown of the formulas and some certain things that you're supposed to know. But let's summarize them. In summary, I'm going to say the following. For ungrouped data, variance is sum of d squared divided by n. Remember, there is no f. And therefore, standard deviation, since we said it's square root of variance, standard deviation will be just square root of whatever formula or whatever figure we got earlier. Then for group data, variance will be equal to sum of fd squared divided by n. Subsequently, standard deviation will be sum of fd squared divided by n. All right? I think I need to say another thing here. Therefore, since d is x minus x bar, this is going to be, this formula is the same as this, as I just indicated earlier. All right? This is exactly the same as that on there. And you can choose that depending on how the one you think is easier or to understand or even use to operate. This formula also, this formula I just indicated a while ago, it's the same as this. So please consider this. Consider that the x bar is just sum of f of x divided by n. And I need to mention one more thing to wind up the summary of the formulas. When you are dealing with a question where you had assumed mean given, it's better for you to use this formula so that you don't have to have lengthy calculations or probably have so many columns added to your table. In this case, the D means deviations from assumed mean. This D here we had at the beginning was deviations from mean, arithmetic mean, but this is deviation from assumed mean. This formula probably is used when we want to avoid getting big values, and that's actually the reason there. The answer will always be the same. Having said that, maybe it's important for us to get to an actual question. Let's start with a question that is a lot easy to handle. The table below shows the number of children per household in an estate, so we are supposed to determine the standard deviation. Well, what we have here is that we have families and we have children. We have the number of children that families have. Only one family had no child. 5 families had 1 child. 11 families had 2 children. 27 families had 3. 10 families had 4, and 4 families had 5, and 2 families had 6 children. All right. So as we get into the calculation, we need first of all to determine the mean value. And what is mean? That was tackled in the first lesson that I did for statistics 2. It is simple. We just need to first of all develop the f of x column, and the f of x column will be gotten by having the x's times corresponding f values. So we have 0 times 1, which is 0, 1 times 5, which is 5, 2 times 11, which is 22, 5 times 4, which is 20, 6 times 2, which is 12, and just that. And again, you add the sum of the f of x's, that is 0, 5, 22, 81, 40, 20, and 12. You get the answer, it will be 180. The sum of f, that is the total number of families. So that way we'll get the average number of children that a family has. And in our case, it is 3. So for the data that I was given, mean is 3. But now we need to go to the actual calculation, which is the standard deviation. And so we need first of all to look for the deviations from the mean we have got. And therefore we need to add another column. We determine the deviations, which is now going to be an additional column, and this is gotten simply by having the x minus mean, that is the x value that you have for a particular class minus 3, which is the mean we got. In this case, we're going to have 0 minus 3, which is negative 3, 1 minus 3, which is negative 2, 2 minus 3, which is negative 1, 3 minus 3, which is 0, 4 minus 3, which is 1, and 5 minus 2, which is 3. Sorry, 5 minus 2 minus 3, which is 2, and 6 minus 3, which is 3. I need to say that these figures are easy to calculate if you look at them this way. These classes are, to get the next value, we just add 1. That means since the first deviation was negative 3, we can always add just 1 to get the next number. So negative 3 plus 1 is this, negative 2 plus 1 is that, negative 1 plus 1 is that, negative 1, the same figure plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. And so that's easy to do instead of having to do a lot of calculations. Having said that, therefore, we need now to get the deviations squared. These ones here, we square the deviations from the mean. These deviations, we square them. Again, we also need to add another column, the f of d squared. That means we're going to have a column for d squared, and again another column for f of d squared, and then after that we'll add them. So this is what I was saying. We have the d's, square them, you get these figures: negative 3 squared, 2 squared, 1 squared. And please, when these numbers are negative, the negative should not show here, because a negative squared is a positive. So that's how we develop this particular column. Why do we need it? Because we need this other one here. And the 9 will be multiplied by the frequency of that particular class. So I'll have 1 times 9, which is 9. I'll have 5 times 4, which is 20, 11 times 1, which is 11, 27 times 0, which is 0, 10 times 1, which is 10, and 4 times 4, which is 16, and 2 times 9, which is 18. And I said here, as I said here, find the sum. Sum of what? F of d squared. So add this on here. My answer was 84. That's easy? I think it is. So basically now we have, I guess, everything that we need so that we can calculate standard deviation and variance. So the first thing, variance will be sum of f d squared divided by n. Do we have f d squared? Yes, it is 84. Do we have d squared? Sorry, do we have the n? Yes, n is 60. Just that. So 84 over 60, 1.4. And standard deviation, therefore, will be square root of 1.4, which is 1.1832. I think that's easy. The only thing that I need to mention here is that whenever we are looking for variance and standard deviation, we need to add, I think, at least 4 columns, almost for every question. In our case, we needed to have the f of x, and then the d's, the d squared, f of d squared. Okay. Alternatively, we can look at the same value. We can determine the standard deviation in an alternative method, and the method I indicated earlier was sum of f of x squared divided by n minus x bar squared, and I think this n should be small letter n, like this case here. Now, what do we do? This formula suggests the kind of columns that we need to have. What columns? We don't have f of x squared here, therefore we must have an f of x squared. To have f of x squared, it means we must have the x squared. All right, that indicates another column, and we have f of x, so we just need equivalent of the d's and d squared. All right, sorry, we need to have an equivalent of the d squared and the f of d squared, and let's go there. The first thing is we need to have the x squared, so that we'll use that to get f of x. So the x squared, this one of course is just the number of children squared. So we'll have 0 squared, which is 0, 1 squared, which is 1, 2 squared, which is 4, up to 6 squared, which is 36. Then I'll multiply the x squared times the respective f's to get these figures here. For example, I have 1 times 0, which is 0, 5 times 1, which is 1, 11 times 4, which is 44, 27 times 9, which is 243, say 4 times 25, which is 100, and 2 times 36, which is 72, and add them. All right, we just add them, and then we get to put the values in the formula. And having added them, you get the formula. Simply, it'll be sum of f of x squared, which is 624, divided by total number of observations, there were 60, minus x bar squared, and that was our mean at the beginning, which is 3 squared. And so putting the values there, you get, it is still the same, 1.1832. You see, you arrive at the same answer, but it depends on what do you want to use and what is making you use that particular formula. For example, if at the beginning you had been told to look for mean, I think it's always fair that you use this formula. I think this probably is easy. I don't know, but you can choose the one that you think you have a reason for. Having said that, I want us to go to a lot more technical question, and there is a question. We're told that the table below shows the distribution of ages in months of 80 from 4s in a school. So determine the standard deviation. All right, that's a table there. We have the from 4s and the number of them. So, sorry, we have the ages and the number of from 4s. We have 2 from 4s between the age of 210 and 212 months. We have 8 of them between the ages of 213 to 215. We have 18 from 4s between the ages of 219 and 221. Only 5 of them were somewhere between 228 and 220 months old. So that's a breakdown of what the table means. Now, to operate that, we need first of all to refresh ourselves. We have 2 formulas, that formula there and that other one there. I want us to use both of them and see how the answers vary and how the calculation vary also, and so you can use that as a basis of knowing which formula that you want to use. But at the end of the day, I think I need to mention this. We might always need to use this kind of formula, the f of d squared, especially if 1, you are given assumed mean, 2, if to reduce the crazy big figures that you could get. To reduce the big numbers that you're likely to get, you might need always use this, and that becomes a lot easier. But if you had been asked to find mean and then standard deviation, you have no option. This will be easier for you. Okay, let's go. The first thing, determine the mean value. That's easy. I think I tackled this again at the beginning. It's easy. You just need to have the f of x's, and f of x is just gotten by multiplying the f's times x's. Someone is probably asking, where does the x come from? X's are averages of the classes. That is 210 minus 212. Sorry, 210 plus 212 divided by 2. Average of this number and this number. The average of this number and this number. So all through, the averages of these ones, these figures here. 228 and 230, if you add the two of them divided by 2, you get 229. Besides, these numbers are such that we have, say, 10, 11, 12. So 11 must be the average. This is 13, 14, 15. And on and on. So I don't need to delve a lot into that. So you get the x's. Now you multiply the x's and f's. All right. So that you get the f of x's. 2 times 211 is 422. 8 times 214 is 1712. 25 times 217 is 5424. 10 times 226 is 2260. 5 times 229 is 1145. So that's it. Determine the mean. Mean again will be sum of f of x divided by sum of f, which is 17,600 divided by 80, and our answer will be 220. Okay, let me not spend a lot of time on how to get mean, since I explained that in a previous lesson. The next thing is we need to get the x squared column. All right, the x squared column, that'll be easy. Just these x's, you square them, you get this one. You see the numbers, they have become really big. 211 squared is 44,521. 217 squared is 47,089. 226 squared is 51,076. 229 squared is 52,441. So these big numbers are very big. But anyway, we go to the next column, f of x. That's the column that we need to have. So f of x, what is that supposed to be? It is the x squared times the respective f. Like 2 times 44,521, which is that number there. 8 times 45,796, which is 368. Say 18 times 48,400, which is 871,200. We have 10 times 51,076, which is 510,760. 5 times 52,441, which is 262,280. Big numbers indeed. Now, of course, we'll need to add them. So square, you add them, we get 3,872, 3,873,548. Sorry for that. Okay, now we use these values to operate a standard deviation. You'll agree with me that these numbers are big and easy to introduce an error because of just human error as you calculate, and we need to be a lot more careful. Another important thing I need to mention, if you know this formula offhand, anytime you're studying over a question, the figures that you have in the formula should suggest the kind of columns that you anticipate to add to your table. For example, in this column we have f of x squared. What does that mean? At least we'll need an x. That is the x column. We will also need an x squared. That's why we have this particular column. We'll also need an f of x. That's why we have this particular column. All right? We also need f of x squared. That's why we have the last column. All right? So you should always know that the formula points to the kind of columns we are supposed to add. Now put these values in the formula. 3,873,548 is f of x squared, n is 80, x bar squared is 220. So there it is. And formula will be, yeah, that will lead us to 48,419.35 minus 48,400 square root of 19.75.35, and the answer becomes 4.4. And that's what you're supposed to do to operate standard deviation. The alternative method, we turn to that now. We could use this as a formula where I said in this case we are going to assume that our assumed mean is 223, and I said that the reason we are using 223, that is the reason we are using assumed means, is because we want to reduce the possibility of getting big figures which are easy to introduce errors. Therefore, we started out this way. Number one, create the D column. We had the classes. These were ranges of ages of the months of the Form 4s. We had 2 Form 4s between 210 and 212. We had 18 Form 4s between 219 and 221, and on and on. Okay? Now we need to have the D's. We had the X's. Now we need to have the D's. The D's is the mean. Sorry, D is X minus X minus assumed mean. And therefore, since we have the X's, we can subtract assumed mean, like 211 minus 223 to get 12, 214 minus 223 to get negative 9, 217 minus 223 to get that, and on and on. And so the last answer will be 6 down there. I think I should mention that since the X's here are such that to get the next X, we're just adding 3. We have 11 plus 3 is 14, plus 3 17, plus 3 20, and on and on. These values are easy also to calculate. Since the first one was negative 12, we can just add 3. Minus 12 plus 3 is minus 9. Minus plus 3 is negative 6. Minus 6 plus 3 is minus 3. Minus 3 plus 3 is 0. Plus 3 is 3. Plus 3 is 6. So that's easy. The next column we need to add is f of d. Sorry. Yes, f of d. Yeah, sorry for that. We need to have an f of d, and there it is. The f of d is just the d's times the f's. 2 times negative 12, which is negative 24. 8 times negative 9, which is 72. 25 times negative 6, which is that one there. 5 times 6 is 30. All right. The next column. What other column do we need? I think we should be able to know from the formula. We already have f of d. We already have the d. We now seem to need another column. We need to have a d squared and an f of d squared. So we start with the d squared. Create the d squared column, which is that in there. The d squared is just the values got for the deviations from the assumed mean. You just square. 12 squared is 144, 9 is 81, 6 is 36, 3 gives us 9, 0 is 0, 3, 9, and all that. And these figures are easy to calculate. You see, they kind of go up to 0 and then start increasing the same way they were decreasing. Another thing I should mention is that the negatives should never feature in the squared, since when you square a negative number, it always becomes positive, right? So having said that, we have the d squared column. Now we go to the f of d squared column, and we also need to sum the values. So there it is, 288, 648, and all that. But how do we get them? We have the f's times the corresponding d squared. So 2 times 144 is 288. 8 times 81 is 648. 25 times 36 is 900. 18 times 9 is 162. 12 times 0 is 0. 10 times 9 is 90. 5 times 36 is 80. And you add them, you get 2,268. Right? We have everything we needed to put in the formulas to arrive at the standard deviation. So this is what we do. Sum of fd squared is 2,268. We got it right there. The n is total number of students. They were 80. Sum of fd is negative 240, and again is 80, and they operate. And that gives us 19 square root of 19.35, which is again 4.4. Pretty easy. We have arrived at the same answer, but this time around we have avoided using those millions that we got in the previous question. Therefore, when we have assumed mean, we can always use this second formula. I should also mention that this formula is the same as the previous one, only that the d is replaced by x. That brings us to the end of our lesson today about measures of dispersion. We're tackling variance and standard deviation. I hope you find it helpful, and this is my suggestion. Please comment about this. I appreciate one person who told me to make a certain tutorial, and I'll be also sharing with you people about it. Please comment, share, and subscribe. I'll even appreciate your corrections. And thank you.